Okay, all right, thanks for coming to my talk. My name is Dave Snowdon, and I'm going to be talking about emotional closure. And by this, I don't mean the fact that you might shed a tear of rage or frustration or happiness as you're writing Clojure. I mean about building emotional things in Clojure and why you might want to do that. So, why? Why am I talking about human or robots, and why do I have this thing here? Why might I want them to be emotional? And why Clojure anyway? So hopefully, we'll get through all these three. So let's start with humanoid robots. Now, why would you want one? And the common answer people give you, it's utility, obviously, right? Because you make them like a human, you know, they can use hands, they can use human tools, right? Obviously. To that I say Roomba. It's cheaper, it works better, it's more reliable. I mean, why on earth would you want a humanoid robot to do your vacuuming when that does it easier? And for those of you who might be interested in robots, you might say, there was a Darpa robotics challenge, and that was particularly to find humanoid robots that could work in rescue situations. Okay. Who in the audience has their arms joined to their hips? Not many, I hope. So, okay, so if not because of utility, then why? And I'm going to say it's the user interface. And what user interface do I mean? I mean other people. The idea why you might want to have a humanoid robot is because you're trying to exploit the user interface that we're used to using every day when we deal with other people. So, you know, the idea being, you know, there should be nothing to learn, right? And that's a picture of my daughter, by the way. I was kind of hoping to get that on the slide. So, there aren't actually that many user interface paradigms, I don't think, that I come across. So, you know, we started with the command line, text. Then we moved on to WIMP, Windows icons, mouse pointer. And mobile's really just a kind of version of WIMP, but you know, with fingers instead of mice. Not new. If you were alive in the late 80s and 90s, we had virtual reality, and that was kind of different. You know, we tried to embody physical things, a virtual space, but you had to go into this virtual space to really make use of it. But okay, it's fine. And now we've got human. Now, hopefully, you're used to dealing with human, but you might not be used to coding for it. And so I think this is quite an interesting time. You know, it's an opportunity to learn to build another style of user interface that, you know, people haven't really done before, at least not very long, and we're not still very good at it. At least I'm personally not very good at it anyway, and I haven't really met anyone who sussed it. So I think it's a great learning opportunity. And the other thing about it is it's social. You know, if I have an app on my phone and my laptop, I have to work pretty hard to make that a multi-user app. Robots are embodied in the world. You don't really have to work hard to make it a social app. It is naturally a social application in the same way that if you put more than two people together, you have a social situation. And so you might think, well, hang on. People have been studying social situations for a while. There might be some people who could help us. And here I'd like to say ethnomethodologists. Everyone here know what an ethnomethodologist is? Cool. Okay, so ethnomethodology, it's an offshoot of sociology, and it's designed with the sort of codes and conventions that people use in various situations. Now, sociology has a kind of bad reputation as being, oh, you know, it's an easy thing that obvious people do, but the sort of curse of sociology, I think, that if they speak simply, everyone goes, yeah, it's obvious, I know that stuff. And then if they write it down what they really mean, you think, oh, I can't understand that. And that's why I really like this fake magazine cover written by an ethnomethodologist who I know, and it's Invasion of the Ethnomethodologists. They wrote impenetrably, and that's often true, I find, unfortunately. But there is a lot of knowledge out there, if you can decode it, on how to make applications or how people work together, how they socialize. And I'm hoping that maybe you can learn to apply that to building applications for robots. Back in a previous life, I tried to learn to apply it to using making collaborative virtual reality applications. With a mix of success, there's still some work to learn. But there's a body of knowledge out there if we can use it. Okay, so you build a humanoid robot. You have the idea of making applications that people will just naturally work with people. Why am I talking about emotions? So, does anyone here actually have a Roomba? Hey, okay, cool. Do you talk to your Roomba? I'm kind of relieved to hear that. My next question will be, if you talk to it, do you expect it to answer you back? Hopefully, again, the answer was no. And that's kind of the point, really, is that when people see this thing, the first thing they do is they talk to it. They go, hello. They look and they come in, they wave at it, they go and shake its hand, and there's a certain level of expectations you have as soon as you make something look human-like that you don't get for a roomba or a washing machine. And you think, well, that's okay, that's okay. But there's also a negative side as well, in that if you don't do anything to make these things emotional, then people don't think, oh, okay, that's neutral. They interpret it as being negative. Neutrality, I think, is not an option. Whatever this thing does, people are going to ascribe to it an emotional response. If he doesn't say hello back, he's like, why is the robot pissed off with me? Doesn't he like me? And you wouldn't go to your washing machine and go, my washing machine didn't say hello. But you would, people do with the robot. And so, you've got to do something. Now, there's a emotion researcher called Paul Ekman, who spent a while studying emotions, and he has a number of things to say, and I probably won't read out the quotes, it might take me a bit too long. But basically, he has a couple of things to say. The first thing he says is that the reason people have emotions is it's a way of understanding what are the things you would need to attend to right now. It's a focusing mechanism. There's a whole bunch of things out there that I could react to. What is it that this should be most important for me right now? And so that could be useful for robots too. But the main thing is really, in order to get this application to this accepted, they have to at least show some sort of rudimentary emotional behavior. So, how might you do that? Now, I've basically started doing this when I started reading a whole bunch of papers about emotions and robots, and I found a paper by a guy called Michael Sellers. I'll put the reference up at the end. And so I didn't produce the model, but I read his paper and thought, well, that sounds kind of convincing. Maybe I can build it. Then that means I really understand it, and then I can see how well does this thing work. And while doing that, I thought, okay, there are a number of things that an emotional model should have. So it should allow it to have multiple feelings at once, right? I mean, if the model's okay, you are happy, you are sad, that's probably not complex enough, because certainly people are much more complex than that. For example, if you have a dog and it dies, you might be sad, and you meet a friend in the street and you're happy. But the feeling of sadness doesn't go away. You're actually feeling multiple things at the same time, and one thing may be dominant, may be obvious, but the other things are still there. So I'd say that a complete model has to have this multiple nature. It's got to learn from experience. You can't take an application in advance and say, okay, this is how you should react emotionally to every possible situation. You just can't do that. So you have to have a way of learning from experience. Like, oh, I touched the flame, that was bad. And finally, it has to be able to make a difference, right? I mean, there's no point having emotions if they don't do anything, if they don't add any value, if they don't make the application behave differently. So, before I actually go and talk about the architecture itself, I'm going to mention Maslow. So Maslow was a psychiatrist, and he published this in the 60s. And the idea basically was that you have a whole bunch of motivations or drives, and they're arranged in a hierarchy. So the things at the low level have to be satisfied before you worry about high-level stuff. And so, at the low level, you have really basic stuff like, can I have air, food, water? If I don't have air to breathe, I'm probably not worrying about too much up here. And then as you move up, you have things like security of your body, of your family, and so on. You get more refined levels up here. And so the idea behind the model I'm using is that you also can stack motivations in this way. So you can say, okay, some things are going to take priority because, if the robot's about to walk off the end of the table, he should worry about that rather than whether you're smiling at him. Okay, skip that. So, how might such a thing look like? I'm whizzing through it here. So, we start off with the world. A world that has things in it. And we have a set of motivations. So these are basic drives that your system wants to maintain. So again, it might be something now just the hunger. If your battery is going to be low, then you want to do something about it. You might be scared. You might have something now just a fear. it being a particularly social robot, it might want to go and meet people, so there might be a drive analogous to loneliness or to sociability. And so you want the idea basically is to keep these things satisfied. So if there's no dissatisfaction anywhere, if everything's completely satisfied, then the robot is perfectly happy. Otherwise, it has to do something to address those problems. Now, from those bunch of motivations, we have an overall emotional state, which is the satisfaction level of each of these motivations. So, we have our world. We're getting sense data from the world. It might be internal sense data like battery levels. It might be from sight. It might be touch. It could be anything. And we have these things I'm calling recognizers that will take sense information and transform that into something that the model can understand. They get passed into the motivations, and I've cut out some lines here just to make it simple, but the idea is basically that every recognizer sends every piece of sense data into every motivation, and it's up to the motivations to decide, is this interesting to me? So the hunger motivation might really only care about battery level and it ignores everything else. The fear motivation might care about particularly, am I about to walk off a table? Am I seeing any obstacles in my way? And so on. And so these motivations, they take input state, decide what they're going to do with it, adjust their dissatisfaction value, and that gets pushed into the global emotional state. But that's only half the picture. As I said earlier, what you really want to do is you want to have an effect on the world. And so you have, I've called them adapters, and things that look at the emotional state and decide, okay, given I'm this way, what do I need to do? And so I've written them as these sort of strange two-halved things here, because part of it is understanding the emotional state, then it's doing something about it, but you're also perceiving the results of that action. So the model can see, it sees not only sense data coming from outside, but it sees what it's doing, and it can reason about that. I moved my arm, oh, that was a bad idea, I won't do that again. Now, I mentioned learning. Now, in this particular model, learning is done using a combination of short-term and long-term memory. And the idea is that things that I've seen recently get stuffed into short-term memory. And while they're in short-term memory, I keep track of how my emotional state changes, positive or negative. And after a period of time, I'm going to start forgetting things in short-term memory, because it is, after all, short-term. And when something leaves short-term memory, I decide, okay, how much of an emotional impact did that have? If it's not much, well, I can forget it. There's no harm done. If it had a significant impact, then I might want to remember that. So I might put that into long-term memory. I've associated, this is what I sensed, this is how I felt about it. And once things are in long-term memory, they can get adjusted. So as more sense data comes in, again, I might have another impression about that. My first impression might have been bad. And the second time, it might be a bit better. So I can adjust contents in long-term memory based on what happens to me. And finally, the final feedback loop is that I can use long-term memory to decide how I feel about things that I've just perceived. So if I see a person, and I've seen that person before, then I don't have to. I can use how I felt about them last time, or the aggregate of how I felt about them last time, to decide how I'm going to feel about them now, how it's going to change my emotional state. Okay, hopefully that's making sense. So, it's probably time for a demo, really. And, of course, being demos, it's time for things that go horribly wrong. So I thought, and robots are as bad as children, actually. You should never work with them. So I thought, I'll show you in advance what hopefully you might see, and then we can keep track and see how much of that we actually get through in the demo. So I'm hoping to show the model reacting to sensory percepts and updating emotional state. I'm hoping to show actions getting selected on the basis of that emotional state. And I'm hoping to show percepts going into short-term memory, and you can see the model evaluating how it feels about each of those things as time goes on. I probably won't get a chance to show you about things getting promoted from short-term memory to long-term memory unless the demo really does start dragging on, because obviously that takes time. So, mouse does not work on this thing. Right, so start up my Clojure application. So John mentioned Leiningen. I'm using Leiningen to fire up basically a Clojure web server. And we'll start up there. And yes, it will get there eventually. Oh, it's syncing Dropbox. How lovely. No wonder it's going slowly. Right. Okay. I should have whipped that. So I thought I found this model quite hard to tune. So one of the things I thought it'd be useful to have was like a way of peering into the robot's mind and saying, how is my robot feeling right now? And so maybe you feel that's kind of creepy, but it seemed like a good idea at the time. So this is the global emotional state. This is its motivations and how unsatisfied they are. You can see that it's getting a bit bored because nothing's happening. And for more debugging information, these are the motivations down here. Now, also, I wanted to show some inputs. So, face recognition. Face recognition is a hard thing because it's really dependent on lighting. And I also had trouble getting Steve and Linus to turn up for my demo. So I thought I'd fake it. Now, first I need to ask the robot what his IP address is.
I'm Robbie. My internet address is 192, 168, 43, 250.
Yeah, so I've just connect my web app to the robot.
I'm starting to feel quite emotional.
Yeah. So let's see what he's doing. He's kind of bored. He's not very scared. Let's see what happens if I show him Steve Ballmer. Come on. Oop. Yeah, still bar's too slow. Let's try showing him Steve Ballmer again. Yeah, so you can see there's a spike of fear there. And these things decay at different rates. So, fear is like, oh, okay, didn't last too long. So let's say, maybe he likes Linus, because he runs Linux, so he should like Linus, right? So what you probably can't see unless I scroll down is that these things, these lots of numbers that mean nothing, have appeared. So this is basically dumping the robot's short-term memory. You can see he's actually at home. He saw Steve, he saw Linus, and this thing here is basically the vector of all his motivations. You can see them gradually getting updated over time. There's not a huge amount happening. Now let's start really annoying him. Let's go and let's poke him randomly. So you can see these are just things he's detecting. He's like that. Oh, let's see, it's back of his head. It's making him scared. He doesn't like that. What else can I do? If I maybe tap his head. Well, that seems to make him annoyed. Something like that. Okay, I'll just keep pestering him. Don't think you like that. Now, the interesting thing is you saw that he got angry, and then the anger just dropped down. And that was because he did this exterminate action, and you maybe just didn't see that. But that he basically, he felt, it made him feel better. If I scroll down to his, where is he? Short-term memory. You can't, I know this is really hard to read, but just trust me, there's one here, he got angry. He did something, and now he feels better. Okay. What else can I show that's actually of any interest at all? He still is a robot with no long-term memory. We haven't been going long enough. It takes about 5 minutes for things to expire. Let's maybe zoom into one of these things in short-term memory. See if I can make that big enough to read. So you can see that while this thing here is when he actually saw Steve Ballmer, he's become a bit less bored, a bit more playful. Okay, he's got a lot less frightened now, but a bit less angry. So overall, he's had although he's seen Steve Ballmer, he's actually feeling quite positive at the moment, which is odd. Maybe he obviously
Is
particularly
anyone there? I'm feeling lonely. Is
Okay.
anyone there? I'm feeling lonely.
Oh.
Ho hum, I'm bored.
Okay, yeah, he's getting quite bored.
Ho hum, I'm bored.
Yeah, okay, that's...
Ho hum, I'm bored.
Yeah, he is... Well, let's maybe show him Steve Ballmer, or let's show him another robot. Maybe that will make him feel less lonely. Oop. But he's still bored. You don't do that. Go on.
Ho hum, I'm bored.
Okay.
Ho hum, I'm bored. Ho hum, I'm bored.
Ah, shut up. Okay.
Nope, nope.
That's the nice thing about robots, you can just get rid of them. Yeah, so I was probably never going to go over to long-term memory. It's just going to take too long. Right. Now, let's find the mice. Back to the side. So, Clojure. I've talked about what I'm doing, and what I haven't explained is what has this got to do with Clojure, and why Clojure? Where's John? It's all his fault. So basically, you normally program this robot in Python. And I'd read this paper, I've started to build this model in Python, and I spent a while at it, and it was going okay. But I hadn't really finished it, and it was, wasn't really enjoying it particularly. And John organised these monthly hackathons called Hack the Tower. And I'd really recommend them if you have a chance to go and see them in London, because basically it's a day where you have the opportunity to go and hack on whatever you want. And so a couple of months ago, I was at one of these Hack the Tower events, and I thought, well, what should I do? And I'm feeling particularly antisocial, so I don't really want to work on anybody else's projects. What should I do? And I thought, well, it kind of be good to brush up some of my Clojure skills. I wasn't feeling that hot at Clojure at the time. So I thought, I know, that motion model I was struggling with, I'll try and build it in Clojure. And so I spent a day hacking at it, and by the end of the day, I was actually feeling quite good about that. So I thought, oh, this is not so bad. So I kept at it. So basically what I want to do really is reflect now on what it was about Clojure that seemed to make that experience good, why I got further in Clojure than I did in Python. And I think there are some things about the Clojure language that make it particularly powerful for a number of reasons. And I want to go further now. And hopefully, if you sat in John's presentation, even if you don't know Clojure, the code sample I'm showing won't be so alien to you. So one thing I like about Clojure before actually showing you code is it has this sort of, what I feel to be sort of this UNIX small tools feel to it. So you start with simple things. As John said, you don't tend to make up complex data particular types. You tend to use the standard data structures and build things composed out of maps and vectors. And that means it's very easy to apply standard functions to your custom data structures, your data structures, because they are just plain vanilla collections, basically. And Clojure comes with quite a number of fairly powerful functions for working on these data structures. So you have a fairly powerful toolbox to work with. And the libraries that you get with Clojure tend to be fairly small and fairly single purpose. I mean, Clojure doesn't seem to have, at least in my experience of it, these sort of large, huge Java frameworks that take ages to understand. And it tends to come in small chunks that we used to get your head around, or used to get my head around anyway. So with that, I'll maybe try and give an example. I'll talk about the threading operator. So one of the problems that you come up from time to time is you have a function that generates something, and you want to pass that result to another function that does something else. That information again passes to another function, and so you could write it like that. I've got 4 functions A to D. They each take a parameter and a bit of data, but that's kind of hard to read. So what the threading operators do is let you say, well, I'm going to take the result of this, pass it to this, pass it to this, pass it to this. And that makes things quite easy to read, as I feel. So you can think of this being here, being hopped in, stuffed in there, the result of that being stuffed in there, and so on. So with this operator, the value is inserted as the first argument, which means the second element of the list, for each thing in the rest of that sequence. And there's a a similar operator which stuffs things in as the last element. So what I want to do is then sort of take that and maybe see how you can use this in practice to sort of transform information. And the example I'm going to use is, actually, again, all these code samples are derived from bits of code in the demo. So this is basically a fairly large sequence of maps. And each map, for example, represents a motivation. Now, the actual maps are kind of much bigger than this. I've cut them down so I can get them on the screen. But they have an ID, they have a name, and various other attributes, including the desire, which I've actually managed to cut out of this, unfortunately. But basically, I want to take something like that, and I want to transform it to that, which corresponds to the overall state that the robot is feeling at the moment. So I'm mapping from this motivation to that its dissatisfaction value, and so on. Now, my first attempt at that involved using Clojure's map function and a fairly horrendous anonymous function. And it worked, it does the business. And then I came across a blog post by a guy called Jay Fields. And he said, don't use anonymous functions in Clojure. And I thought, why? They're so easy. But his argument was basically that they're too easy, right? That it's very easy to reach the anonymous function to do this arbitrary bit of transformation. But Clojure already provides a whole toolbox of functions that do exactly that. And if you use the toolbox, then other people have more of a chance of working out what your code is doing than if you just start stuffing things together in random ways. And so basically his point was like, okay, you can use anonymous functions, but use them as a last resort. Try and use the toolkit, the standard toolkit first. And so I thought, well, okay, maybe he's right. It sounds like a reasonable argument after all. So I threw away my first implementation, and I came up with something like that. Now, John was talking about documentation, so he'll be happy to see that I do have a documentation string there. So basically, it takes one argument, which is a list of motivations, which again is just a big list of maps, and uses the threading operator I showed to stuff those through a number of transformations. Now, to make it easier, because I couldn't work this out the first time, I thought let's break that down a bit. So we'll define motivations to be that big chunk of stuff. And then the first operation is I'm going to map. A map just takes a function and a collection and applies that function to everything in that collection. And the function here is juxt, which is a standard Clojure.core function. And I'm passing it two keywords, ID and desire. And what that would do, basically, it will build me a function that will pull out the values associated with those keywords from everything in every map in that sequence. So I get back this. So now I have a sequence of two-element vectors. Okay, so that's close. So I can see the ID and the value, but it's still not quite what I wanted. So step 2 is I feed the results of the first step into this. And what this is doing, it's applying hash map, which takes its arguments and turns them into a map. Because I'm using a list rather than applying those arguments, I use apply, and partial basically generates a function that takes some number of arguments less than the full complement, and basically gives me a function that just takes the remainder. So then I get this. So I'm now down to a sequence of maps, which is fine, but what I wanted was one map. So that's the last stage here. So I apply merge, and then that basically takes a sequence of maps and gives me one map. Now, that's quite cool. I mean, I perhaps don't get the thrill of writing anonymous functions and thinking, wow, I'm using Clojure, I'm really cool. But at least anyone else who's familiar with Clojure.core has probably as good a chance of understanding that as they did my original version. And it helps me also learn more about Clojure.core as I'm going. The other thing I found about Clojure that's really cool is destructuring. So Clojure had this sort of mini DSL built into it that's used for pulling apart collections. And you can use it in many places. You can use it for function arguments, in let blocks, in the for structure as well, I think. And it's kind of nice. So, I mean, a lot of times in Java, you get past a collection, and you just want to pull bits out of it. And Clojure makes it really easy to do that. So let, I don't think John covered let, is basically a way of binding values to local symbols that are evaluated in the rest of the block. So I've got a vector containing 2 elements, and maybe I want just to pull out the values. I want to bind them to different variables. So I use this expression here. I pass a vector of symbols, and Clojure will bind x to 1, y to 2. And I can do other things as well. I can say maybe I really only care about the first one, and then whatever is left. So I can use this to say, okay, I'm going to bind x to 1 and x's to everything else. And I can go further. I can say, okay, I want x, I want the rest, but I still want a reference to the original thing that was given to me, because maybe I need to pass that to someone else. And so you have this as directive, which basically binds everything to the whole original sequence that's passed in, vector that's passed into me. And it's not just vectors you can do that with. You can do that with maps. So in the same way, I can have a map of things. So foo is mapped to 1, bar is mapped to 2, and so on. And say, okay, I want a symbol, foo val, that's mapped to whatever the value of foo is in the map that has been given to me. But that's kind of cumbersome. I don't really want to have to write foo val when I want the value of foo. So there's a keys directive that says, okay, these are the keys I want to pull out the map. Go and pull them out and bind those values to things the same name as this. So basically a symbol without the colon. So that means I get back to foo being mapped to 1, bar being mapped to 2. And again, as with vectors, I can still keep a reference to the original map if I wanted that. And that's surprisingly powerful and it's surprisingly useful. I mean, there's lots of times when I'm writing code when you just want to pull bits out of connections. And this makes it really easy to do that without writing code to go, okay, if I'm going to take the second item in the list and so on. Okay, so I've actually got more time than I expected. So Core.async is not part of the core Clojure language, and I'm not going to have time to go too heavily into depth of it. But basically, it's built along this idea by Hoare back in the 1980s called communicating sequential processes. And the idea is that you can model a system as a collection of processes, and I don't mean processes in the operating system sense, I mean logical threads of execution, and you can combine them together. So it's sort of the, in the same way to loosely coupling pure functions, you have, in a sense, pure processes that know nothing about their external environment. They get information from channels, and they push information out of channels. And you can build up arbitrary directed graphs of these unidirectional channels. And Clojure makes it, Core.async makes that relatively easy to do. And what's more, it makes it relatively easy to do in an asynchronous way. Under the hood, it's all using asynchronous logic. Basically, and so I won't go into this with nearly as much detail as I like, but if you check out YouTube, there's some excellent videos by a guy called Tim Baldridge, he's one of the authors of Core.async. And he has videos that start from the sort of, what is Core.async level, right down to, here's how I built it using Clojure macros, and here's how these macros work. And it's really quite interesting. But a quick summary anyway of what it does is that you have channels that abstract communication, and these are they're thread local channels. They're not channels over the wire. They're just channels, logical channels. And so you have a function chan that creates a synchronous channel, and you can also have other types of channel as well. So you can have buffered channels, channels that drop older input when they become full, channels that drop new input when they become full, and so on. But the basic channel is a thing that contains one item and it's synchronous. So you push one thing in, you can't push anything else in until you've taken one thing off. And then you have a number of operations. So you have sort of standard asynchronous calls like put and take. So put something onto a channel, take takes it off, and it calls the callback you supply when it takes it off. And that's a paradigm, not unfamiliar to use things like Netty if you use that, or JavaScript callbacks. But where things get more interesting is when you have these operators. So these put and take, but they block. But the interesting thing is the way in which they block. So these versions here, the double bang, they actually block a thread. So they're actually standard. They need a heavyweight thread. Whereas these things do not block threads. They need to exist in something called a Go loop, or a Go construct. And that's really where the cleverness of Core.async comes into play, in that you can write code that looks like it's blocking, but it's not. And this Go here is a macro, which means that at compile time it rewrites the code that you supply, and it rewrites it in such a way that under the hood it's using callbacks. It actually sort of builds a state machine, effectively. But you can write something that looks like it's blocking. But because it's not actually using real threads, you can have thousands of these things and not suffer any performance loss. And so what I'm doing here basically is I'm looping. I'm pulling values out of this channel called input and stuffing them into state. And then if some predicate is satisfied in the state, then I might push things onto an output. And again, it looks like it's blocking, but actually under the hood, it's not. And you can get a bit more complex than that. So suppose one of the things that the demo does is it accumulates sensory information over a period of time, and every 2 seconds or so it goes, okay, now I need to reevaluate my emotional state. And it does that using the current state plus all the things it's accumulated over that period of time. And so I have a loop that looks a bit like this, where I have a timeout channel. So timeout is just a function that produces a channel that does nothing apart from send me a value after the specified time, and then it closes. And I can use alts to listen on multiple channels at once. So I'm going to listen on timer and consultancy, which I assume have been passed in from elsewhere. And what alts bang gives me is a value and the channel that value came in on. So I can check, okay, did things come in the command chain? All right, so I'm just going to conjure them to my list of commands and recur, so go back to the loop. And then eventually when the timer will fire, I come here. So now I have a list of commands, potentially, that I can do something with them, and then I'll recur with it and create a new timer. And that's probably all I've really got to do, time for to cover with Core.async. But it's pretty cool, actually. And the other nice thing about it is it works on Clojurescript, which is kind of interesting because that's Clojurescript is I want to say a few words about next. So Clojure is basically a dialect that runs on the JVM, but there's an equivalent dialect, Clojurescript, that runs on JavaScript. So it basically compiles to JavaScript using Google's Clojure compiler. And it's kind of nice to be able to write the same code on the client and the server. So in the demo I showed you, the web page was basically actually written in Clojurescript. So all the evaluation was happening in Clojurescript for generating the moving graphs and so on. So that's kind of cool. And I don't know, anyone here heard of Facebook's React framework? Okay, a few. So what's interesting about React is you can view it as a framework that lets you build user interfaces by building components which are basically pure functions. So you take the current state of your application, you pass it to a pure function, and that generates a DOM tree of what the output should look like. And you think, well, that's going to be horrendously inefficient if every time my application state changes, I'm producing this huge chunk of DOM. And so what they do to make that fast is they actually you render to a virtual DOM, and then they have a very fast diff operation that does the diff between the virtual DOM and the real DOM, and only applies those changes. But it means that your components can be really, really simple, and they don't have to worry too much about managing state. Now, David Nolan wrote something called Om that basically wraps React in a Clojurescript wrapper. And that takes advantage of the fact that Clojure's data structures are immutable to make even more aggressive optimizations. And he has a particularly interesting blog post where he shows things like garbage collection behavior on the same application, but one written just using pure React and one written in Om. And And the interface is exactly the same, but the garbage collection behavior is quite different. So it's often combined with Core.async. I mentioned small libraries earlier, and there's a particularly nice small library called Cord by a guy called James Henderson. And what that does, it wraps WebSockets to look like Core.async channels. So you can write your application split across the client and server, exchanging state over Core.async channels, and that state could get passed back from the server to the client, or from the client to the server, but the components generating that state don't have to know. As far as they're concerned, they're just stuffing information into a channel and getting it out. So I'm just going to follow up with a very quick example of a Om component. And so this is nothing like doing it justice, but we'll try anyway. So basically, this is a component. It implements a render protocol, which means that when its state changes, the render function is called. Is actually passed with the current component state, which we don't care about in this case. And what this does is it builds a div, and then takes the value of this collection VA, and builds a whole bunch of subcomponents, bar view, and passes them some options. And every time the state changes, it'll get called. But as I said earlier, because React has this virtual DOM and does diff, if things don't change, then the actual real DOM won't get updated. Other nice things. Oh yeah, so you can see I'm using Destructuring here. This thing here, C, is a big map. I'm just putting out the part of the map I care about. And Om has a relatively nice thing called cursors, which lets you pass bits of the overall state to a given component. So components don't have to see the whole state of your application. Right, I'm getting nearly out of time, so I'm going to just summarize. So hopefully you believe me when I say that you can treat humanoid robots as another UI paradigm. But the fact that we do that, we build humanoid robots, gives people fairly high expectations, and which means we have to work to fulfill them. And as my demo may have shown, that it's actually non-trivial to do that. It's even more non-trivial to get it working, even. I said, yeah. And, but I think Clojure and Clojurescript do provide some fairly powerful tools for building interesting applications. And hopefully, I've given you a small flavor of that. So you can get the code and laugh at it. It's on GitHub. And the paper that the model is based on is this one here by Michael Sellers. So I'll leave that up, and I'll take questions, if you have any. No, I guess not. Well, in that case, I'll give you... Oh.
How many people has the robot killed?
Well, he's tried to exterminate several people, but unfortunately, just saying exterminate doesn't really kill anyone. So 0. Anyone else? Hi.
Does your model involve any kind of probability? I mean, does it involve fuzzy logic of some kind, or is it just decaying numbers all the time?
So there is some probability in there. It's not using fuzzy logic at all, but it can, when it decides to take actions, they're probabilistic. So it basically it will look at it will apply a probability and decide, okay, given my current state, the probability of doing this is Y, and then decide whether it should take an action or not. So it's not completely deterministic. Cedric.
I see you're using your model to make the robot feel things, but could you use this model to make the robot understand my feelings?
Potentially. I mean, there has been a bunch of work where people have tried to implement models of emotion and use them for empathy. There's some people in Spain, I think, where they try to make an empathic robotic chess player. So they'll play it with children, and the robot will try and understand how the child might be feeling. And they've run a number of studies with the robot being completely neutral, competitive, so going, ha, I'm beating you, or empathic, saying, oh, that was a bad move, would you like to try again? And unsurprisingly, the children kind of like the empathic robot best. So yeah, you probably could use something like this to model empathy. I haven't tried doing that though. Okay. Well, I'll give you 6 minutes back then. Thank you, everyone.